Hello everyone. In this section, we're going to discuss how to quantitatively evaluate the advantage of pricing for different segments. In particular, we're going to approach this problem from two perspectives. First, we're going to look at graphically how segmentation pricing works, that is, charging different prices to different customer segments. Second, once we understand the problem visually, I am going to show you analytically how we find out the optimal prices when we charge one price or two prices. In this topic, you're going to see a lot of numbers, equations, symbols, and you are even going to see some derivatives from your calculus class. Yay! First, let me start with the graphic illustrations. Let's imagine we have an airline, and the airline is trying to decide what price to charge for a ticket. In the first scenario, the airline would only charge a single price for every single seat on the plane. So here is the demand curve. You may recall from our willingness to pay lecture that the demand function that we are showing here really represents the willingness to pay of customers in the market. Here, you see the demand function as demand equals 390 minus 0.1 times price. So what does this mean? This function here establishes the relationship between the horizontal axis, that is x, where the price is, and at that price point, what is the y-axis, that is what the demand is. Let me first explain the extreme conditions under this demand curve. First, what happens when you price at zero? This is straightforward. According to the demand function, when price is 0, 0.1 times 0 is still 0. So it's 390 minus 0, that is, the demand would be 390. So when price is 0, demand is 390. What this really means is in this market, even if the air tickets are free, you can only sell 390 tickets. Next, let's look at the other extreme when demand is 0. So when demand is 0, at what price level do we observe a zero demand? Again, we go back to the demand function. Demand equals 390 minus 0.1 times price. If demand equals 0, what is the price point? If the left-hand side of the equation is 0, in order for 390 minus 0.1 times price to become 0, price should be 3,900. So that gives us the endpoint here that price is $3,900. The demand drops to 0. Alternatively, we can interpret this number, $3,900, as the maximum willingness to pay in the market. That's the point when the last customer drops out of this market, then you have zero demand. So the demand function is pretty convenient. For example, if we have a price level, let's say $100, at $100, what is the demand? So visually, what we see here is at $100, if I project a vertical line up, it intersects with the demand curve, and then I project horizontal line to the left, and that is the demand at $100. So the demand is 380 when the price is $100. And in this example, we're going to assume 100 is the variable cost. So it never makes sense for the airline to charge a price below $100 because the more tickets they sell, the more they're going to lose if they charge below the variable cost. Okay, now we have established what the demand curve is and how we calculate demand based on the price level. A single optimal price visually would look like this. Let's say the optimal ticket price is $2,000. At $2,000, what is the demand? When we substitute 2,000 into the demand function, we can calculate that 0.1 times 2,000 is 200. 390 minus 200 is 190. So the demand at the optimal price is 190. Next, we're going to calculate the profit, that is the maximized profit at the optimal price level. We're going to use the function that we have introduced before. That is profit equals price minus variable cost, and that's the margin, and times demand, and then that number minus the fixed cost. In this case, we don't consider the fixed cost. So now we substitute the numbers into the profit function. Profit equals the price of $2,000 minus the variable cost of $100, and that times the demand of 190 tickets. What does this calculation mean visually? Let's come back to our drawings on the demand curve. So let's consider the profit calculation. We have the price, $2,000. We have the variable cost, $100. And then we have the demand, 190. So we have 2,000 minus 100, and that times 190. So by now you probably have figured out, well, this calculation looks like the size of the rectangle. So you have the width on the horizontal axis, that is 2,000 minus 100, and you have the height, that is 190. Visually, the maximized profit at optimal price is the size of this rectangle area. So that's the maximum profit when you charge a single price. Let's take a further look at people with different willingness to pay on this demand curve. Now the price is $2,000. On the right of this price, what if someone is willing to pay $2,500? So $500 above $2,000, this person would happily pay for the ticket that is priced at below his willingness to pay. What about someone who is willing to pay below the price level, let's say $1,500, on the left of the optimal price? Well, this person's willingness to pay is below the price charged in the market, so this person will not be able to purchase the ticket. So this person is not served. One important thing to note here is if we can charge this person $1,500, it would still be profitable for us to sell the ticket. The only problem is if we charge a single price, we cannot go that low. So this person is in fact profitable, but we are not serving this person. A quick recap, the single pricing strategy has two problems. The first problem is it leaves money on the table. Some customers are willing to pay more than the price you charge. The second problem is what we call passed up profit. For the passed up profit, these are the people whose willingness to pay are high enough to be profitable, but not high enough to be above the single price we charge in the market. So both are lost opportunities for the company. It means we are losing profit potentials. How do we solve the problem then? First, let's take a look at the total profit potential if we could charge every single customer his or her willingness to pay in the market. The demand curve represents the willingness to pay of many customers. Remember the assignment we did, drawing the staircase of willingness to pay that represents the overall demand curve. So, the demand curve represents all kinds of customers with different willingness to pay levels. If we could charge each one of them their willingness to pay, it means we charge this customer close to $100. And we charge this customer higher than $100. And each customer here, we charge a higher price, and each customer receives a different price. At the end, the customer with the highest willingness to pay, we charge $3,900, or right below $3,900. And then we charge each customer a different price, and that price is set at the customer's willingness to pay. If that's the case, what is the total profit potential for this demand curve? By now, you probably have figured out the total potential is actually the size of this triangle. That is, everybody is charged at the willingness to pay. And recall the single price scenario. you are only getting a small rectangle out of this big triangle. And if we look at the single price case, this is our profit. That's 50% of the big triangle. This is the money left on the table. This represents 25% of the big triangle. And finally, this is the passed up profit. It represents another 25% of the big triangle. So when we are charging a single optimal price, we only get 50% of the total profit potential. Can we do better than this? Next, let's look at a scenario where we can charge two different prices. Let's say a business class and an economy class. And let's say the two optimal prices for business class and economy class are as follows. First, we charge the business class $2,633, and we sell at that price 127 seats. And this is our profit from the business class. And the next, we charge a lower price on the economy class, $1,367. And the demand we receive from the economy class would be 254 minus the customers already served, 127. So this segment is the demand for the economy class. And the profit from the economy class is the size of this rectangle. Although we still have money left on the table, keep in mind that in this case, money left on the table involves the sum of two triangles. And we still have passed up profit. But visually, it seems like we're doing better because the passed up profit is getting smaller and the money left on the table seems to be getting smaller as well. Visually, here's a comparison between the profit charging a single price versus the profit of charging two prices. Single price profit, total profit of two different classes. It's not hard to tell that visually, the comparison is the single price profit is less than the profit from two different prices. So that is the value of segmentation pricing. If you can segment customers and charge them different prices, and the total profit you are going to receive is going to be higher. I hope by now visually I have convinced you that two price is better. But how much better? This is why I want to introduce the analytical method. This method will help you quantify the level of optimal prices, how to find them, and the level of maximized profit at the optimal prices. Again, we start from the visual representation to establish the calculations. For convenience and generalizability, I'm going to use letters instead of numbers to represent the demand curve. So demand equals A minus B times price. Here, A and B are both representations of two different numbers. And then here we have the variable cost C. If we charge a price here, we're going to have a demand of A minus B times that price level. And in this case, notice that when price is 0, A minus B times 0 would be A. That is, when price is 0, that point on the vertical axis would be equal to A. On the other end, when demand is equal to 0, you can easily calculate that the price level when demand is equal to 0 would be A divided by B. So these are the two endpoints for the demand curve. So they are going to be useful for our later calculations. And of course, the profit would be the size of this rectangle. Going back to the earlier example, where demand equals 390 minus 0.1 times price, in that example, we have A equals 390, B equals 0.1, and C equals 100. So when you see a new demand function and variable cost, you can simply substitute A, B, and C with a new set of numbers. Here are the steps we take to calculate the optimal price and maximize the profit from a single optimal price. First, we express the profit function in terms of price. Second, we differentiate profit function with respect to price. And then we set that derivative equal to 0 and solve for price. Here are the specific steps I take to calculate the optimal price. First, demand equals A minus B times price, and the variable cost is C. And profits is equal to price minus the variable cost times demand. That is the size of the rectangle. Again, in this case, we do not consider the fixed cost. Next, we substitute in the demand function. We have profit equals price minus C times the demand, that is A minus B times price. And then if you open up this calculation, this is the result. You have negative C times A plus B times C, and that number times price, and minus B times price squared. Keep in mind that A, B, and C here are simply numbers. These letters are here for convenience of calculation. So this calculation established the relationship between price and profit. This is a quadratic function, if you may recall. So the relationship between price and profits is an inverted U. That is, when price starts to increase from the variable cost, the profit will go higher because profit margin goes higher. But at some point, when higher price leads to enough demand drop, profit would start to go down with price. So it's an inverted U shape, which is why we want to take derivative to find the top of this U-shaped curve. We take derivative of profit with respect to price. So for that derivative, the constant would become 0, and the linear term would simply take the coefficient A plus BC, so A plus BC, and then minus B price, the quadratic term, would take this 2 to the front, and this 2 would minus 1. So then this term becomes minus 2b times price itself, and set that to 0. In this function, keep in mind that price is the only unknown. This is the optimal price we're trying to solve. And A, B, and C, and B here, they are simply numbers. We're carrying these letters representing the numbers. Therefore, the optimal price is A plus BC divided by 2B. And since we already know that for the demand curve, that demand equals 390 minus 0.1 times price, we have A equals 390, B equals 0.1, C equals 100. So we substitute these three numbers into the optimal price calculation. We have 390 plus 0.1 times 100. So it's A, B, and C. And then divided by 2 times B, that is 0.1. And that's a straightforward calculation. You get the optimal price is $2,000. And for the purpose of this class, I need you to understand the process to get optimal price. For practical purposes, we are going to simply apply this optimal price directly when we see a new demand function. So here is an easier way to remember the formula for the optimal price. I can rewrite the optimal price equation to this form. So why do I write it this way? Because this is an easier way to remember. Recall that on the demand curve, we have A divided by B. That is the maximum willingness to pay. And then we have C, that is the variable cost. So A divided by B plus C divided by 2 is the optimal price. In this formula, the single optimal price is simply the middle point. It's the center between the maximum willingness to pay of A divided by B and the variable cost C. Now let's tackle the next problem when we charge two prices using a customized pricing scheme. So the two prices we charge are price L, that is price low, and price H, that is price high. At price high, we have the demand at price high, so it's A minus price H. And at price low, and then we get a demand of A minus price L. Keeping in mind that it's important to be aware that the demand at low price is not A minus B times price L, because that would be the total height to this. Because the business class customers already served, so this part of the customers are out. And then the economy class customers are actually the distance between here and here. So it will be this demand minus this demand, the height here. The steps we take include, first, to express the profit function in terms of the two prices, high price and the low price. Then we take two different derivatives. So we differentiate profit with respect to high price and low price. Then we set the two derivatives to 0 and solve for the two prices simultaneously. That is, we have two equations and two unknowns. Specifically, here's how we conduct the calculation. Again, the demand curve is demand equals A minus B times price. We lay out the profit by adding up the size of the two rectangles. So we have price H minus the variable cost times demand H. And then we have price L minus variable cost times here demand L minus demand H. So that's the size of the orange rectangle. Next, we substitute the formulas. We take two partial derivatives. First, profit with respect to the high price. Second, profit with respect to the low price. Here, then, we have two formulas, and the two unknowns are price high and price low. So two equations, two unknowns. We can solve that. Please pause the video and try to calculate price L and price H based on the two equations above. After calculation, the two optimal price levels are optimal price high is equal to 2 times A divided by B plus C divided by 3. Price low is equal to A divided by B plus 2C divided by 3. Again, there is an easier way to remember this formula. Keep in mind that the two endpoints are A divided by B, the maximum willingness to pay, and variable cost. So the two optimal prices we have here, they equally split the distance between the maximum willingness to pay, A divided by B, and the variable cost C. So these two prices split this whole segment into 1, 2, and 3 equal segments. The formula can be looked on as 2/3 of A divided by B and 1/3 of C versus 1/3 of A divided by B and 2/3 of C. With the optimal price formula here, and we know the demand is equal to 390 minus 0.1 times price, and the variable cost is $100. So A equals 390, B equals 0.1, and C equals 100. We substitute in these numbers, and then we have the high price is equal to $2,633, and the low price is equal to $1,367. And the maximized profit is calculated using the earlier formula by substituting in the two optimal price levels. We have this calculation with all the numbers substituted in. Punch in the numbers, you'll get that the total profit is $482,000. In summary, here's a comparison between single class and two different classes in terms of pricing. For single class, the optimal price is $2,000, and we sell 190 tickets, and the total profit or contribution is $361,000. For two different classes, business and economy class, we have two different optimal prices at $2,633 and $1,367. And we sell 127 tickets for each class. And the total number of tickets sold is 254. So 254 versus 190. So you actually sell more tickets. And at the end of the day, the total contribution or profit for two prices as a result of segmentation is $482,000, representing a 33% increase in profitability. That's our discussion on pricing by segments. Thank you. I'll see you next time.